All right, let's look at 2.7. It's going to be dealing with absolute value inequalities. So this is going to be putting absolute value equations and linear inequalities together. So let's just recall two ideas, or a few ideas, from each of these problems. So when it came to inequalities, a really big thing to remember is that you have to switch the inequality every time you multiply or divide by a negative. Super important. And then when it came to understanding what inequality was, remember the open side is the bigger side, the closed side is the smaller, right? Closed is smaller, open is bigger. And whenever you're getting something that's bigger than 0, you're implying that you want it to be positive. Smaller than 0 means it's negative. Just a recap on that. And that's for inequalities. A recap for absolute value. Remember that the outcome is either going to be either positive or 0. Those are your only outcomes you can have. So that means once you isolated the absolute value, you had to watch out for negatives and 0. The negatives were because since the only answers is either a positive or 0, if your absolute value is isolated and it's equal to a negative, we know that that cannot be a solution. Whereas when it's equal to 0, you can still get a solution, but you only end up with one solution. When it was equal to a positive, that's when we had to create two separate equations. And we're going to be using all those ideas for absolute value inequalities. So here are some steps that we can follow. So borrowing from absolute value equations, you want to make sure you isolate the absolute value. Just like how we did with absolute value equations. And I also said, once isolated, look out for negatives and 0, right? The same thing we did for absolute value equations, we have to watch out for absolute value inequalities. And now, even more so than before, and you're going to see with some of the examples why. It's not just going to be about if it's equal to a negative, there's no solution. Because with inequalities, there's multiple solutions. Because you're just looking to be either larger or smaller than a number, it's going to make the answers interesting, but we'll see some examples. Now, when we're solving absolute value equations, once we were done isolating, we wrote two separate equations. But since this is inequalities, we're going to write two separate inequalities once it's isolated. And there's no negatives or 0. Because when it's negatives or 0, you can come up with an answer almost without doing any work. Sometimes you might have to do a little, but you can come up with an answer with almost doing 0 work. And I'll show you some examples of that. But when you write those two inequalities, one, just like in the absolute value equation, is going to be positive, and then one's going to be negative. But the fact that we're dealing with inequalities, one's going to be positive, when you change the sign, that's going to trigger this idea for inequalities that you're going to have to switch the inequality because the sign is changing for the number. Almost as if you multiplied or divide by a negative. And we'll see an example of that. And once you do these two equations, they're just going to be, each one of those equations is just going to be a normal linear inequality. Sorry, when you write those two inequalities, you'll have two separate linear inequalities that you can solve. So, hopefully that's a quick recap of just things to remember. Now let's start with this example. So the example is just 2 times the absolute value of 6 minus m minus 3 less than 7. Now remember, step 1 is we have to isolate the absolute value first. We're going to do that by adding 3 to both sides. That cancels my 3's. And that leaves me with 2 times the absolute value of 6 minus m. It's going to be less than 10. Be careful, we are not isolated just yet. I am going to divide both sides by 2. On the right, it simplifies and leaves me with the absolute value of 6m. 6 minus m. Closed absolute value is smaller than 5. Now, I haven't multiplied or I haven't divided by a negative. That will trigger a switching of this inequality. And then I said, once it's isolated, look out for any negatives or zeros. So on this right-hand side, that's not negative and that's not 0. So I'm going to go right into my 2 separate inequalities. So there's going to be one here and one on this side. So like I said, there's one that's going to be the positive. So positive 5, it looks like nothing changes. And then I'm going to have one that's going to be 6 minus m. But then that 5 is going to become a negative 5. But because I'm switching the sign of that number, I am going to switch the inequality as well. And the idea is because you're looking for the absolute value of something that is smaller than 5. And whenever you take the absolute value, remember that could either you can plug anything in here. The outcome is going to end up being positive. So that's going to create different answers. But this, instead of you trying to think about this intuitively, making these 2 separate inequalities does make it a little bit nicer for you. So now I'm going to start with this equation on the left-hand side. That's going to give me, I'm going to subtract 6 on both sides. I'm trying to squeeze it in, sorry. So that cancels. That's going to leave me with negative m is smaller than negative 1. And now I am going to divide by negative 1 on both sides. And because I'm dividing by a negative, that's going to trigger the idea of switching the inequality. And negative 1 divided by negative 1 is positive 1. Now, on the right hand, the second one, maybe I'll just split it this way so it doesn't look super crammed. I'm just going to split it here. I'm going to do the same thing. I'm going to subtract by 6 on both ends. That leaves me with negative m is greater than negative 11. But once again, dividing by that negative 1 on both sides. On the left, simplifies to a positive, but that triggers me having to switch my inequality, and I'm left with positive 11. Now, I have to graph this solution. Now, if you read the book or if you see videos on this, normally you're taught to memorize. Once absolute value is isolated, you know what type of solution you're going to get. You might get a solution that's similar to a compound inequality, which is these that we did. So compound inequalities are when your solutions are in between. And there's going to be some situations where you get 2 separate inequalities. And you're usually taught to memorize when it's smaller or when it's larger what answers you're going to get. But I truly try not to memorize too much because I tend to forget the more I have to memorize. So I try to follow the same procedure for all problems. The only thing is my final answer, if it's a compound inequality, I rewrite these two separate inequalities into one. And I'll show you what that looks like in a second. Everything's a little compressed. Hopefully I can get my graph to fit. So here, so I only have two numbers to reference. So the two numbers I have to reference is 1 and 11. Now if you remember for inequalities, because both of these m is strictly bigger than 1, meaning that m cannot be equal to 1, that leaves me with a open circle at 1. And similarly with 11, I have an open circle. But if I were to read this says m has to be bigger than 1. And where are the numbers bigger than 1? They're bigger on the right. But what are the numbers that are smaller than 11? They are on the left. So that leads me to find that my solutions are actually between 1 and 11. And because of this, that tells me that this is a compound inequality. My answer is not two separate inequalities. I am going to have to take those two and rewrite them into a compound inequality, which into just one, saying that my variable is bigger than 1 but smaller than 11. And usually, like I said, if you look at a book or a video, sometimes they will have you memorize that because you're looking for something that's smaller than this number, you usually rewrite it into a compound inequality right from the beginning. I prefer to do it towards the end after you can read your solution. So it's like give and take, whichever works best for you. But that would be my solution from, and I can write this in interval notation as well. So let me move this up a bit. Sorry for cramming it in there. But from 1 to 11. And I use parentheses because 1 and 11 are not part of my solution. Now let's try this next example. So this one, it's quicker to simplify in the sense all I need to do is divide by -2 to both sides. But once again, I'm dividing by a negative, so that's going to trigger the fact that I need to switch the inequality. That's why I talked about it right at the beginning. It's right the first ones we're looking at, which is switching the inequality whenever you divide or multiply by a negative. Because for these examples, there's going to be a lot of switching that goes on. So now that I've switched it, this says the absolute value of x plus 1. And now, because it's isolated and there's no negative or 0 on the left, I can create my two separate inequalities. So one with my positive inequality, and then one with a negative inequality. But I switched not a negative inequality, but a negative number. But because the sign is changing, so will the inequality change as well. Now on the left hand side, all I need to do is simplify, isolate my variable, subtract by 1. The 1 cancels, and I'm left with 1 is smaller than or equal to x. And same thing on the right, subtract by 1. That's canceled on the right. That leaves me with -3 has to be bigger than or equal to x. Now once again, if I sketch this graph, I have two numbers of reference. That's -3, +1. Now, just squeeze this in here. Looking at these inequalities, the value of x cannot not only is it bigger, but it also can be equal to 1. And because of that, that reminds me that I can have a closed circle. Similarly with -3. Because it can equal -3, I now have a closed circle. I keep using the wrong pen. But now reading this says x, so that's the equal to part, is a closed circle. But it says x needs to be bigger, meaning the open side. So being bigger are the numbers to the right. And then x has to be smaller than -3. So those are numbers to the left. And because my answer isn't in between, it's outward, I don't have to rewrite a compound inequality. I can leave my inequalities as each one individually because there's two separate intervals. But I can still write one general solution, which would be from -infinity, stopping at -3. I use a closed bracket because -3 is part of your solution. And then I can union from 1 to +infinity. And this would be my graph, and this is my interval notation. Let's continue. So once again, here's another example. If you guys want to pause at any moment, you can to try these problems. That works fine. Once again, all I need to do is isolate my my absolute value. The 3's is simplified. That leaves me with absolute value of 5 minus x. Close absolute value. Smaller than or equal to 4. And I keep saying this, once it's isolated, watch out for zeros or negatives. Because that's going to make a huge difference when it comes to the amount of work you have to do after that, which is almost no work at all. And I think the next example illustrates that. So because it's isolated now, I'm going to create our two separate inequalities. Since I have a little more room here, I am going to write them on this side. Or I think I can fit them here. I can do 5 minus x is less than 4, or 5 minus x, and because I have to switch this to -4, I have to switch this to bigger than or equal to -4. Now it's probably best that I actually write, I need more room for these. I'm going to write them up here. Oops, not enough room for some of these. I'm going to write one here. Let me group them a little bit closer together to save some space. So we'll start with this first one. I'll create a little space. So I'm going to subtract 5 on both sides. The 5's cancel. Normally, you don't really want to subtract here at the bottom, but I don't have the space. You usually want to make a subtraction on a straight line, like -5 here, -5, but for the sake of space and time, I'm writing here at the bottom. So -x less than or equal to -1, and now I have to divide by -1, which means I'm going to have to switch my inequality to greater than or equal to +1. Then same thing, I'm going to subtract 5 to both sides. That leaves me with -x. And once going to be greater than or equal to -9. And now again, I'm dividing by a negative, so that means I need to switch my inequality for a second time. Now you want to be careful, because you might be asking, wait, didn't I go from less than or equal to 4 to greater than or equal to -4? And yes, because you have to write a positive and a negative one. And the negative ends up switching the inequality. But because I divided by a negative, I had to switch the inequality again. And that's why I wanted to recall that multiplying or dividing by a negative causes that switching of your inequality. Because we're going to be doing that a lot here. Now, let me draw a number line. So there's only two numbers to reference. I have 1, and then I have 9. Because they both are equal, I can have closed circles at both of them. And now I just have to read it. This says x has to be bigger than 1, so that's on the right. This says x has to be smaller than the 1, that's on the left. So that tells me my solutions are in between. So I actually have to rewrite, because this is a compound inequality. I can't leave it as two separate inequalities. And because it's written nicely for me already, I know I can write just 1 is less than or equal to x, less than or equal to 9. It's organized for me here on the number line. That makes it nicer for me to write this compound inequality. And once again, if I want to write interval notation, it's brackets 1 to 9, and then close brackets again. Now, let's illustrate that example of once it's isolated, so my absolute value is isolated, but the other side is 0. So whenever I said once it's isolated, you need to watch out for negatives and 0. And the reason why, because if you try doing two separate equations, doing work, it might throw your answer off. But you have to read what this is asking for. There's two things. This is asking for numbers that are smaller than 0, which I did say, what does it mean to get a number smaller than 0? It means that you're looking for something that's negative. But let's not forget, whatever I plug into this x, then it gets subtracted by 5. The outcome is always going to be positive. So it's actually going to be impossible for me to ever satisfy the inequality portion of this problem. Because smaller than 0 is negative, and nothing in here has ever come out to be negative. But remember we said the outcome of absolute value could either be negative or 0. Now, can I get a 0 out and it's equal to 0? Now that is possible. And if I think about this, x minus 5, what value of x is going to give me that 0? And it's going to be exactly positive 5. And I don't bother graphing this, because if I graph it, I'm really only graphing a dot essentially. And I can write my answer in set notation, meaning that x is the only number that satisfies this equation. Now, there was a little bit of work to be done, but most of it was through intuition. Now, let's do this really quick next example, which I'm going to subtract 3 on both ends. And this is going to illustrate another one of those 0 and negative problems. So that cancels. I'm going to let negative absolute value of x plus 2 is smaller than 4. But then if I divide by -1, two things are happening. One, I need to change the sign. The inequality is going to become bigger. And then 4 divided by -1 is -4. But don't forget, I'm still inside these absolute values. Now it's isolated. But if you notice, On the opposite side, there is a negative, and I did say, look out once isolated. Look out for negatives and 0. Now let's pay attention to what this is asking for. Now, this is asking for numbers that are bigger than -4 or equal to. Well, I can already, from the very beginning, get rid of this equal to portion because the outcome of absolute value can never be negative, so it'll never equal -4. But, can I get answers that are bigger than -4? Now we have to think, because the outcome, I can plug anything I want into the absolute value. But the outcome is either going to be positive or 0. Which if you think, well, any positive number, again, anything after 0, is positive, and that's going to be bigger than -4. And on top of that, 0 is further to the right of -4, so 0 is already bigger than -4. So because all the outcomes are either positive or 0, that tells me my solution is going to be all real numbers. Or you can say negative infinity to infinity, because I plug in -2, that gives me 0. The absolute value of 0 is 0. Now, I'm never going to be able to equal, but I don't need to satisfy the equal to. I just need to satisfy one of them. It's greater than or equal to. And 0 is bigger than -4. And every other solution is going to be positive, and all positive numbers are bigger than -4. Well, there's some work involved here, very little. But I never created my 2 separate examples. If you do, you will get to some answer, but it's not meaningful because it starts as an absolute value, and we have these properties about absolute values. So hopefully that made some sense. You can always recap this and see how it does for you.